What's up everybody, and welcome to part 6 of my Basics of Deep Learning series. In the previous videos we have answered the first question of how the deep learning algorithm makes a decision. Namely, we put in our input data in front of the neural net and then we feed it through all the layers until we reach the last layer, which then produces the output of the neural net. And this process was then accordingly called feed forward. So now we can start to tackle the second question here, which was how do you determine the right parameters for the algorithm? And for the deep learning algorithm, the parameters are the weights, which are represented by those lines here. So now determining the right parameters means that we want to find such weights that the neural net is able to make correct predictions. Therefore, obviously, it would be helpful if we had a metric that exactly tells us in a precise and concrete way how good the neural net actually is at making predictions. And in the context of deep learning, such a metric is called a cost function or a loss function. So what we're now going to do is we're going to create such a cost function. And one simple approach for doing that is to simply calculate the error. So we're going to subtract the label from the output. So let's say for this neural net here we have determined the outputs of 4 examples. So the output matrix is going to be a 4 by 1 matrix, and then accordingly the label is also going to be a 4 by 1 matrix, and then we can simply element wise subtract this matrix from that one to get this error matrix. And here the error is going to be 0 if our prediction is correct. So if the output and the label are the same, and if those predictions are not correct, then the error is going to be either 1 or -1. And now, since we want to have a metric that tells us overall how good the neural net is at making predictions, we simply sum up all those errors. So this sum of the errors we could now use as our cost function. But as you can see in this example calculation here, even though we predicted two of our examples incorrectly, the error nonetheless is still 0. So this doesn't really make any sense. And that happens because the error of those wrong predictions here, the 1 and the -1, they cancel each other out. So to get now around this problem here, we have to make sure that the errors of such incorrect predictions are always positive, so that they then can't cancel each other out. And one way to do that is to simply square this subtraction here. So instead of just calculating the error, we're going to calculate the squared error. And if we now do that for those matrices here, then you will see that this -1 here disappears, and then our metric actually indicates that there is some error associated with our predictions. So this sum of the squared errors we could now use as our cost function, but there's also a problem with that, and it's not really a problem but more of a slight inconsistency, because the more examples we're going to have, the bigger the sum of the squared errors is potentially going to be. So for example, let's say we have determined the outputs of 10 examples, and let's say that we predicted 3 of those examples incorrectly. So in that case then the sum of the squared errors is accordingly 3. So the neural net in this situation here seems to be worse at making decisions or predictions than the neural net in this situation. But if you then actually look at those errors here, then you can see that actually here we have predicted 70% of those examples correctly, whereas here we only predicted 50% correctly. So actually the neural net in this situation here is better at making predictions, and accordingly the metric or our metric that we use should indicate that. So to make sure that that's the case, what we're going to do is, instead of calculating the sum of those squared errors here, we're going to calculate the mean of those squared errors. So we're going to divide this 2 here by the number of elements that we have in this matrix. So we divide it by 4, and this will then give us a mean squared error of 0.5. And this 3 here, we divide by 10, because that's how many examples or elements are in this matrix here. And that gives us then a mean squared error of 0.3. So now our metric actually indicates that the neural net in this situation here is better at making predictions than the neural net in this situation. Okay, so now before we actually write down the formula for this metric, let's think about how we can calculate it when our neural net is not having just one output node, but instead if it has several output nodes. After all, that's the neural net that we want to apply to the ice flower dataset. So let's say for this neural net we also predicted 4 examples, and then in this case the matrices are going to have 3 columns instead of just 1. But this doesn't actually change anything about this calculation here. So we can again simply subtract the label matrix element-wise from the output matrix, and then we square that to get this squared error matrix. And then just like before, we take the sum over all those examples. And now here is a difference, because before we had just a regular number, or in linear algebra terms a scalar, but now we are still left with a vector. So what we have to do now is we have to take another sum, and this time it's the sum over all those nodes here. And in this case we get then a 6, and this 6 then we divide by all the elements in this matrix here. So we divide it by 12, and this again gives us a mean squared error of 0.5. And one thing I would like to point out here is that this 0.5 doesn't indicate that this neural net, the neural net in this situation is equally good at making predictions than the neural net in this situation. Because as you can see, here we only predicted 1 out of 4 examples correctly, whereas here we predicted 2 out of 4 examples correctly. So the mean squared error doesn't, what I want to point out is that the mean squared error doesn't represent the proportion of correct predictions, which is the impression you might have gotten when we just looked at the examples with 1 output node. The mean squared error, just like the name says, represents the mean of the squared errors. And here, for each incorrect prediction, we get 2 ones and not just 1. And because of that, it just so happens that the neural net in this situation here also gets a mean squared error of 0.5. So one thing to keep in mind is that when working with the mean squared error, and if you want to compare 2 neural nets directly with each other, you have to make sure that they have the same number of output nodes. Okay, so now having said that, let's write out those calculations here in a formal way. So first, we are subtracting the label matrix from the output matrix, and then we square that subtraction. And after that, then we take the sum over all the examples E, and after that, then we take the sum over all the nodes N. And here actually the order of those summations wouldn't matter, because you could also just take first the sum over all the nodes and then the sum over all the examples, and the result of that would be the same. So you could actually switch up the order of those sigmas here. And then finally, what we're going to do is we're going to divide the sum here by the number of elements in this matrix. So we divide it by the number of elements times the number of nodes, the number of output nodes that we have. And to make this formula a little bit more concise, we're going to represent the numbers of the elements in this matrix here with a capital N. And this capital N just means that we multiply the number of examples that we have with the number of output nodes. So this is now our final metric that we're going to use as our cost function. And remember, our initial goal was that we wanted to find such weights that the neural net is able to make correct predictions. So what this now means is that we want to find such weights that the mean squared error is minimized. So the question now is, how do we do that? And well, if you look at this neural net here, then you could get the impression that it consists of clearly distinguished successive steps, where we first calculate the hidden layer inputs by multiplying our input matrix with weight matrix 1, and then after that we put those hidden layer inputs into the step function to get the hidden layer outputs, which we then multiply with weight matrix 2 to get the output layer inputs, and those then we again put into the step function to get the outputs of the output layer, which are then the output of the neural net. And those outputs then we are going to put into the function or the formula of the mean squared error together with the label to see how good those predictions actually are. So you really could get the impression that there are these clearly distinguished successive steps, but since we are always putting the result of one step into the next equation or into the next step, we could actually represent all those individual steps in just one big function. So we could also write that the mean squared error is x multiplied with weight matrix 1, and this then we put into the step function, and now this expression here we multiply with weight matrix 2, and now this whole expression we then put again into the step function. So this whole expression now represents the output of the neural net, and this then we put into the formula for the mean squared error. So this single function now represents all those individual steps. And again, our goal was to make sure that the neural net is able to make correct predictions. So what this now means is that we want to find the minimum of this function here. Or in other words, we want to find the specific values for the variables of this function where the function is minimized. And I don't know about you, but maybe that reminds you of something that you've learned in school. Because one of the few things that I vaguely remember from high school math is something called derivatives, and that we could use them to find the minima or maxima of a function. So now let's look at a simpler function than our mean squared error to refresh our memories of the concept of a derivative. So let's say y is a function of w, and it looks like this. So w squared plus 2 times w plus 3. And if we plot this function, then it looks like this. And now to denote the derivative of this function, we can either write f prime of w, which is Lagrange notation, or we could also write dy over dw, which is Leibniz notation. And in the context of deep learning and backpropagation, I personally prefer to use Leibniz notation. So that's what we're going to be mainly using moving forward. Okay, so now let's actually write down the formula for this derivative. And therefore, we're going to use the power rule for this first expression here. So we bring down this 2 in front of the w, and then we reduce the exponent by 1. So we are only left then with w raised to the power of 1, which is just w. And then for the second expression, we again use the power rule. So we bring down this 1 here in front of the w and multiply it with this 2. And then we again reduce the exponent by 1. So we are left with w raised to the power of 0, which is just 1. So we are only left with this 2 here. And now for this last expression here, since the derivative of a constant is always 0, we don't actually have to add anything here. So this is the final formula for the derivative. And what it tells us is the slope of this function. So the slope of this graph here for any given point. So for any given w. So let's say w is equal to 1. In that case, if we put that 1 into this equation here, then we can see that y is 6. So in the graph, we are at this point here. W is 1, and y is 6. And then if we put this 1 into the equation for the derivative, we can see that the derivative or the slope at this point is 4. And a way to visualize that is to plot the tangent line for this graph at this point. This straight line here also has a slope of 4. And what the slope tells us is how our y changes if we change our w by a certain amount. So let's say we would increase our w by 1, so we would move from 1 to 2. Then in that case, the y would increase by 4, so the y would increase from 6 to 10. But if we only increase our w by 0.5, then our y would increase by 4 times that 0.5. So the y would increase from 6 to 8. And now, however, for our function, the slope is not constant, as is the case with this straight line here, but it is always changing. So here, for example, the slope is relatively flat, but then it gets steeper and steeper. So what the derivative of this function actually tells us is the instantaneous rate of change at this particular point. So at this particular w. So the derivative tells us how our y changes if we increase our w by a tiny amount, almost 0. So in this case here, when w is 1, then y will increase by 4 times that tiny amount. And at this point here, when w is equal to 0, if we increase the w by a tiny amount here, then y will only increase by 2 times that amount. And at this point here, when w is 3, y will increase by 8 times that amount. And if we go to this other side here, where the slope is negative, then accordingly the y will decrease if we slightly increase our w. So to summarize, what the derivative of a function tells us is how our function will change if we slightly increase the variable of that function. And hereby it gives us 2 pieces of information. The first one is the sign here of the derivative, and this tells us the direction of the change. So is our function going to decrease or is it going to increase? And then the second piece of information that we get from the derivative is, or comes from this actual number here, and this tells us the amount of the change. So will our function or y increase by a lot, or will it increase only by a little? And in my opinion, this is the most important concept to understand for how backpropagation works and what it does. So now that we know what derivatives are and how they work, let's think about how we can use them to find the minimum of a function, which is why we introduced them in the first place. And here the idea is also relatively simple, and maybe you also remember it from school. And namely, if you look at this graph here, you can see that the minimum is right here at this point. And at this point, the slope is 0. So if we set the equation for the derivative of this function equal to 0, then we can solve it for w and find a specific value of w for which the function will reach a minimum or a maximum. So let's do that now. So therefore, let's bring this 2 over to the other side, and then we're gonna divide both sides by 2. And then we get the solution that w is equal to -1. So when w is equal to -1, then the derivative of the function is 0, which means we are at a minimum or a maximum. And as we can see in this graph here, we are actually at a minimum. So this, for example, now is one way how you can determine the minimum of a function. And this way of doing that is called an analytical approach, because we are taking the derivative or the equation for the derivative of the function, and we are setting it equal to 0. and then we solve it for w by algebraically manipulating this function in such a way that the w is isolated on one side. But there are also cases where we can't determine the minimum of a function with this analytical approach. So for example, if our initial function would look like this, and the corresponding graph then would look like that, and if we then write down the equation for the derivative of this function, it looks like this. And if we set this function equal to 0, then we can maybe bring over this 1 here and then factor out 1w, but then we are kind of stuck and we can't isolate the w on just one side. So for this function here, we can't determine the minimum with this analytical approach. This obviously now begs the question, how do we then find the minimum of this function? Because in the graph, we can actually see that there is a minimum for this function. And the answer to that question we are going to cover in the upcoming video. So thanks for watching, and hopefully I will see you in the next video.